All right, welcome everyone. So for today, just a few announcements before we get started. So we have homework for Learning Outcome D2 due tonight, so on the product rule and quotient rule. And then we have on Thursday, we have the homework for chain rule due, so that's D3. And then for today, after lecture, I'll be posting your graded exams on Gradescope. So just something to take a look at. And then for recitations today and this week, you can go over any questions. So if there's a question you missed on the exam, you can go over with the TA to see exactly what you missed. Also, go back to our old lectures and see how we did. So most of those problems on the exams were, very similar to a homework question or to an example we did in lecture. So go back in our old lectures and see what we did. Find a problem that's very similar and see what we did and what work we did and the notation that we used. So that's just another reminder. And like I said, in recitation today, we can go over any questions. So if you have questions on the homework, questions on examples from lecture, if you have questions on the exam, you can go over any of that. All right. So for today, we're going to be looking at more differentiation, but this time we're going to be talking about sort of a new type of function that we probably haven't really seen too much before. So today in Learning Outcome D4, we're going to see how to compute derivatives of implicitly defined functions and then use those derivatives, just like we've been doing, to find the slope of the tangent line, but now to an implicit curve. All right, so let's kind of first introduce the idea. We see this terminology implicit. Let's first talk about what that means. All right, so when we talk about functions, what we've been talking about for what you've probably seen in most of your math courses are equations involving two variables. And normally we use x and y. Maybe we use some other variables, but for the most part, when we talk about an equation, there's two variables, x and y. And so when we have an equation like that, what we're very familiar with are what we call explicitly defined functions. And this is basically every function we've worked with so far. You've probably, in all the math courses you've ever taken, any function you've worked with has probably been an explicitly defined function. So here, the variable y is explicitly written as a function of x. So as an example, we might have something like y equals x squared minus 1. So there we see two variables, y and x, and it's in the very similar format of y on one side, y equals, and then all the x terms on the other side. And so when we look at this equation, we see y equals is explicitly stated in the equation. It's y equals, and then only x's are on the right. So that's what we're used to, is when we have an equation of two variables and it's defining a function, we're used to talking about it in the form y equals a function of x. But there's other types of equations out there, and we can think of them as defining a function as well. But for these, variable y is going to be implicitly defined as a function of x. So it's not going to be directly written. We're not going to have a formula for what y actually is. So an example of something like this might be x squared plus y squared equal to 4. As it's written, that's an equation of two variables, x's and y's, but it's not in that form y equals. maybe there's some work we could do to get it into that form, but as it's written, it's not in the form y equals. So we would consider that equation as being an equation that implicitly defines function y. We're not directly told what y actually is. Now, with these two example curves, we've graphed them. One of them's a parabola, the other one's a circle. And if we look at these curves, we might be interested in particular points on those curves. And in each case, it still makes sense, though, to talk about the slope of the tangent line. So if we look at both of those, in both cases, it still makes sense to talk about the slope of the tangent line. And we know what the tangent line is, and we've graphed a few tangent lines in each of those, or we've graphed a tangent line in each case there, and we know what the tangent line, the slope of the tangent line is. It's directly related to the derivative, dy dx. So when we have an implicitly defined function or an explicitly defined function, it still makes sense to talk about dy dx. And so all the rules that we've seen so far have gone into, this is how we differentiate an explicit function. And the technique we're going to learn today is, well, how do we differentiate an implicit function? And so as we look at these two example curves here, the parabola on the left and the circle on the right, you might be thinking about the vertical line test. So when we talk about functions, for a curve to define a function, the curve has to pass the vertical line test. And for explicit functions, there's usually not an issue. It passes it. And we see that this parabola passes the vertical line test. Now, with a curve or an equation that defines an implicit function, we have to be a little bit more careful when we consider the curve. And so in the case over here with the circle, we can still think of the circle as passing the vertical line test, provided we only consider a portion of the curve. So we're going to be interested in, when we talk about a tangent line, normally we're talking about a specific point. And so if we look at near point P here, if we look at the portion of the curve near point P, that portion of the curve, if we forget about everything else, that portion of the curve does pass the vertical line test. So when we have an equation that's giving us an implicit function, a lot of times we have to only look at a piece of the curve and then forget about everything else. All right, so let's kind of get into the how this procedure is going to work, and then we'll see some more examples of these types of equations and more pictures, just to kind of develop more of an understanding for what it means to be an implicitly defined function. All right, so let's first look at the process that we're going to go through. So we have an equation with two variables, x and y, and we want to calculate dy dx. So when we see x, we're going to think of x as just a variable. So in our equation, and maybe the equation to have as a little example here, let's say we have the equation x squared plus y cubed plus xy equal to 3. And we're interested in calculating the derivative dy dx in relation to that equation. So when we look there, we see x, and x is just our regular old variable. So whenever we have a term involving only an x, what we're going to do is we're going to differentiate that term just like usual. So in our little example here, the x squared plus y cubed plus xy equal to 3, that x squared term, that's a term involving only an x. So anytime we see something like that, we're just going to differentiate it just like we normally would. So all of the regular derivative rules apply. Now, whenever we see a y in our equation and we're going to differentiate it, we're going to treat y like two things. We're going to treat it as a variable, and we're going to treat it like a function. So we're thinking of y as both a variable, but we're also thinking of it as a function. It's a function of x. So when we see a term involving only a y, it's kind of a two-step process for how we differentiate it. We're going to differentiate it like usual, and that's the variable part. So we're thinking of y like a variable. So whenever we see a variable, we differentiate it like usual. But because we're also thinking of y as a function, we have to do a little bit extra. And that little bit extra is we're going to multiply the result by y prime. So in our little example equation here, x squared plus y cubed plus xy equal to 3, if we were going to differentiate that y cubed part, that's a term involving only a y. And so the way we would differentiate that is we would differentiate it like usual and then multiply the result by y prime. All right, so let's see why we do it this way. So let's consider two little examples. Let's say we wanted to differentiate the function f of x equal to x to the power 4 plus 3, all cubed. Now we've done things like this. This involves chain rule. And what we would do to get our derivative f prime is, this is just general power rule. So we would bring down the exponent 3, keep the term inside the parentheses exactly the same, subtract 1 in the exponent. So we have 3 times x to the 4th plus 3 squared. Then we take the term inside the parentheses and we multiply by its derivative. So we take the inner function and multiply by its derivative. So the first part there of our chain rule is like our usual power rule, and then the second part is where we multiply by the derivative of the inner function. So we've used chain rule to differentiate that function f of x, just a regular explicit function there. But now let's suppose we wanted to differentiate the expression y cubed, and here we're thinking of y as both a variable and we're thinking of it as a function of x. We're really thinking of it as a sort of a secret function of x. There's x terms hidden inside the y. So to really emphasize that, we might rewrite y cubed. So to emphasize that y is a function of x, we might write it in function notation. So like we had f of x, we might rewrite that as y of x. So it'd be y of x cubed. So then to get the derivative of that, it would be very similar. We would use the general power rule. We'd use the chain rule. So we'd bring down the 3, keep what's inside the parentheses exactly the same, subtract 1 in the exponent. So we get 3 times y of x squared. But because there's an inner function, we have to multiply by its derivative, y prime of x. And so normally we don't write this kind of extended notation here. We don't write y of x, we just kind of keep it as y. So if we just simplify our notation back, this would be 3y squared, and then the y prime of x we would just write as y prime. So when we see it, as we're going to do these, when we see a y term, we're treating the y as both a variable and a function of x. So there's a little bit more we have to do. We're going to differentiate it like usual. So if it's power rule, use power rule. And then once you get that usual result, you're going to multiply by y prime. And sort of the behind the scenes there is there's chain rule going on behind the scenes. All right, and then finally, if we look in our equation and if we see a term involving both x's and y's, so we have like x, our equation was x squared plus y cubed plus xy equal to 3. That third term there on the left, the x times y, that's a term involving both an x and a y. So if we see any terms like that, then you might have to use product rule, like we would have to here. Maybe you have to use quotient rule. So if it was like x divided by y, so if you saw multiplication of your x and y terms, you'd use product rule. If you saw a fraction or division, you would have to use quotient rule. So maybe something like x divided by y. Or if you saw an inner function and an outer function, you might have to use something like chain rule. So maybe something like sine of x plus y. There we see an outer function sine and then an inner function x plus y. So if you have a term involving both x and a y, all of those derivative rules that we learned before might come into play. All right, so let's see how this process works. So let's try the example x squared plus y squared equal to 4, equation of a circle. And we can think of y as being implicitly defined as a function of x. And in some cases, in this case, we actually could solve for y, but that's not really necessary here in order to calculate dy dx. So let's see how this process works. So we're going to write down our equation, x squared plus y squared equal to 4. And the first step of implicit differentiation is just to calculate the derivative of each term with respect to x. So we're going to apply the derivative to each term here in our equation. So that's step 1. And then we calculate the derivative. So derivative of x, this is an x term only. So there's only x's in that x squared. So we're going to differentiate it like usual. So derivative of x squared, just like usual, would be 2x. Now the next term, that y squared, it's a y term. So we have to do a little bit extra. We're going to differentiate it like usual, but then we're going to multiply the result by y prime. So derivative of y squared is 2y. And then we're going to multiply that result by y prime. So we do the derivative like usual. So regular power rule gives us the 2y, and then we multiply that result by y prime. And then on the right, derivative of 4 is just a constant, so that's just 0. All right, so there, we're done differentiating. Now what we want to do is we want to calculate dy dx, so ultimately we want to solve for y prime. And that's really all the last of these steps are doing, is the rest of this is just solving for y prime. And so just a little bit about the notation here. Sometimes it's easier to use the shorthand prime notation. Really, that just means apply the derivative with respect to x in this case. And so when we talk about y prime, that's the same thing as dy dx. So when you're doing these implicit differentiation problems, a lot of times it's a little bit easier just to use more of the shorthand prime notation. But if you want to use d dx, that's fine as well. All right, so we applied the derivative to every term. We actually calculated the derivative. And so now we have the equation 2x plus 2y times y prime is equal to 0. And so the rest of our work here is going to be solving for y prime. So step 2 says move all terms with y prime to the left-hand side. And y prime's already there on the left. So we're done with that. There's only one term with y prime in it. It's that 2y times y prime. And so anything without y prime, that 2x term doesn't have a y prime, we want to move that to the right-hand side. And so the way we move it to the right-hand side is with subtraction. So we're going to subtract 2x from both sides. So when we do that, we get 2y times y prime is equal to negative 2x. So now all of our terms with y prime are on the left, and all the terms without y prime are on the other side. And so the fourth step says, let's factor out that y prime. So on all the terms on the left, let's factor out a y prime. And so it's going to be helpful to, not too much work there to do for this problem, but it'll be helpful to think of it as 2y times y prime. And so what we're going to do next is we're going to divide both sides of our equation by that term in front of the y prime. So we're going to divide both sides by 2y. And so when we do that, we get y prime is equal to negative 2x over 2y. And then the 2's cancel. So we're left with just negative x over y. And that's our derivative. That's dy dx. And that's as far as we're going to go. So when we actually, for implicit differentiation, a lot of times when we calculate the derivative itself will be in terms of x and y. And that's fine. So we went through all our steps here, and we found that y prime was equal to negative x over y, and that's perfectly fine with implicit differentiation. Normally we do get a result that's in terms of both x and y. All right, so we found our derivative. Now let's use that to actually find the slope of our tangent line, the slope of the graph at a point on the curve. So let's see how this would work. So we're interested in this case of the slope at the point 1 comma square root 3. So slope of the curve, we have our curve here. This is x squared plus y squared equal to 4. And we have our point 1 comma square root 3 that's on the actual curve. And we've actually drawn in the tangent line there. So how do we find the slope of the tangent line? Well, that's where our derivative comes in. So we're going to take our derivative dy dx, the one that we just calculated, and we're going to evaluate it at our point. So let's just remember, we found that dy dx was equal to negative x over y. That's what we found just in the last part there. And so what we're going to do is we're going to evaluate that derivative at our point. And when we look at our point here, the x-coordinate is 1 and the y-coordinate is square root 3. So when we evaluate our derivative, we're going to evaluate it at x equals 1 and y equals square root 3. Those are the numbers that we're plugging in. So wherever I see an x, I'm going to plug in 1. So I'm going to get negative 1 on the top. And then wherever I see a y, I'm going to plug in square root 3. So I'm going to get a square root 3 in the denominator there. And there's my slope. and it's negative, and that agrees with what we see in our tangent line there. Our tangent line is going, it's moving down, and it has we see that it has a negative slope. So that kind of agrees with what we see there on our curve. We see that it has a negative slope. All right. Let's try another example for this implicit differentiation. Just take some practice. So let's go through the process again, but this time for the equation x squared times y to the 6 equal 1. And we're going to use implicit differentiation to calculate the derivative dy dx. So first thing we do, we write down our equation and we apply the derivative to both sides. So we go along and we differentiate each term. Very first step there. Now when we look at that left-hand side, what we see here is that this x squared times y to the 6, this is a term involving both x and y. So there's some x's and y's in that term. And so specifically, it's x squared times y to the 6. So when we differentiate it, because there's multiplication there in the middle, we have to use the product rule. So for those terms that have both an x and a y kind of right next to each other like that, you have to use one of our old derivative rules, whether it's a product or a quotient or maybe another chain rule. So let's see how this would look. So we're going to differentiate that x squared times y to the 6 using power rule. So how we actually implement the product rule is we write down our product, 2 copies of our product. So x squared times y to the 6. X squared times y to the 6. We put a plus sign in the middle. And then in the first copy, we apply the derivative to the first part of our function. And then in the second copy, we apply the derivative to the second part of our function. And that's product rule. So that's just applying the product rule. Now on the right side of our equation, it was equal to the derivative of 1, and 1 is just a constant, so the derivative is 0. All right, so we have this equation now. We still have some derivatives to do, so we're going to keep going. But now when we look at this, we need to do the derivative of x squared, and this one is the derivative of an x term only. So when we differentiate that, we're just going to differentiate it like usual. So derivative of x squared is 2x. And then the y to the power 6 is outside the brackets, so we keep that the same. Then we have plus x squared. That's outside the brackets, so we keep that exactly the same. And then we get to another term that we have to differentiate. And here it's y to the power 6. And this is a y term only. So inside the brackets there, we only see y to the power 6. There's only y's in there. So when we differentiate it like usual. 6 times y to the power 5. So just basic power rule. And then because it's a y term, we multiply that result by y prime. And then we're done differentiating. So that's equal to 0. So we're done with all the derivatives. Now all the work that's left is to solve for y prime. And a lot of times this is where it gets a little bit more complicated. So all of these other steps, this is where we're solving for y prime. And to help with this, let's just clean up the equation just a little bit. So we'll write this as 6x squared y to the 5th times y prime equal to 0. So it helps just to kind of order things up. Put constant terms in front, that sort of thing. And so for step 2 of this process for solving for y prime, it helps to go through and identify all the y prime terms, all the terms that have a y prime in it, and maybe box it up just to write and say this is a term with y prime, and we want to move all of those y prime terms that we see to the left-hand side. And so for this one, it's already on the left. We're done with that. So that's good. Any of the other terms, we want to move everything else to the right-hand side. So this 2xy to the power 6, there's no y prime there. So we want to move it to the right-hand side, and the way we do that is with subtraction. So we're going to subtract it from both sides. So that gives us the equation 6x squared y to the power 5 times y prime is equal to negative x times y to the power 6. And then we kind of really want to factor off, a lot of times we'll have a bunch of terms on the left there, but we only have the one. But it's still helpful to kind of think of, we're factoring off, we're pulling off that y prime. We're sort of separating it a little bit. And we want to move all of those other terms, the 6x squared y to the 5th, we want to move those to the other side. And so the way we do that is with division. So we're going to divide both sides of this equation by 6x squared y to the 5th, and that's going to get us y prime by itself. And we're done. We've solved for y prime. We have what the derivative, that's dy dx. Now the only thing we might want to do is see if we can simplify that down a little bit. And in this case it does. So a lot of the x's and y's cancel. So if we simplify, again, not really necessary, but it's helpful a lot of times to simplify. So first thing we notice is that the 2 and the 6, there's some common terms there. So when we simplify those, we'll have a 3 in the denominator. Then we have an x on the top, and we have 2 x's on the bottom. So some of those x's will cancel, and that will leave us with an x in the denominator. And then we also have some y terms that are going to cancel. So there's 5 y's on the bottom, and there's 6 y's on the top. So those are going to cancel, and we're going to be left with a y term in the numerator. So all told, and I'll put the negative in front. So all told, we end up with our derivative. It simplifies down to just negative y over 3x. So sometimes we get a little lucky there, and there's a bunch of simplifying that we can do. All right. So in this example, we saw a term that had both x's and y's in it and saw how to handle that. Now let's put it all together and try an equation where we see some x's, and then we see some terms with both x's and y's. And that's what we're going to do in this example. We have the equation x squared times y plus x times y cubed minus 2x equal to 6. And we're going to do implicit differentiation to calculate y prime. So first step, we write down our equation. And we're going to go through and we're going to apply the derivative to each term. So each term that we see on the left, each term that we see on the right. And then we calculate each of those. And when we look at these two terms here, we have x squared times y, and we have x times y cubed. Each of those is a product. So when we do those, we're going to use the product rule. So we're going to use the product rule for this first term, and we're going to use the product rule for that second term. So let's see what the product rule would look like. So let's start with x squared times y. It's a product. So we're going to write down 2 copies of that product. Put a plus sign in the middle. In the first copy, we apply the derivative to the first part of our function, the x squared. In the second copy, we apply the derivative to the second part of our function, the y term there. And so this is what we get after we apply the product rule to that first term. Now, what do we get when we apply it to the second term there? Well, let's kind of go through product rule again. It's x times y cubed, so we're going to write down 2 copies of our product, x times y cubed, x times y cubed, put a plus sign in the middle, apply the derivative to the first part, apply the derivative to the second part there. And so this is what we get when we apply the product rule to the second term in our equation. All right, so we had to use product rule for both of those. Now, if we go to our third term, this one's not so bad. This is just a 2x that we want to differentiate. So there's only x's there. So we're just going to differentiate that like usual. So derivative of negative 2x is negative 2. And then on the right side of our equation, we're differentiating 6. Derivative of a constant is just 0. So negative 2 is what we get from differentiating our third term. All right, so we applied the derivative to each term in our equation. Had to do the product rule for the first 2. Now we keep going and we keep differentiating. So in our, going back to the beginning of our equation, we have x squared prime. So inside those brackets, there's only x's. So we're going to differentiate those like usual. So derivative of x squared, if we do it like usual, is just 2x. And then we have y outside the brackets, so that stays just as y. Then we have plus x squared. And then we're going to do the derivative of y. And so the derivative of y is 1, and we multiply that result by y prime. So we get 1 times y prime, or just y prime there. So that's the product rule for our first term. Then we keep going. We have x prime. So derivative of x is just 1. So I won't write the 1. So that'll just be y cubed. Then we have plus x outside our brackets. So we just leave those alone. And then we differentiate the y cubed. Now this is a y term. So we're going to differentiate it like usual and then multiply the result by y prime. So derivative like usual is 3y squared, and then we multiply the result by y prime. And then we have the minus 2 equal to 0 there. All right, so we have our equation. Let's clean it up just a little bit. Not too much to do here, but I'll just kind of put the constant term first there. So we'll write that one part there as 3x y squared times y prime. All right, so we're done with all the derivatives. Now we just want to solve for y prime. So what we do is we go through and we identify all the terms that have a y prime in it. So we have that x squared times y prime. We want to keep that on the left. We have the 3xy squared times y prime. We want to keep that on the left as well. And then all of these other terms, we want to get those out of there. We want to move those to the right side. So to get the negative, or to get the 2xy over to the right, we're going to subtract it from both sides. To get the y cubed over to the right, we will subtract the y cubed from both sides. And then to get that negative 2 over to the right, we will add 2 to both sides. And so when we write down what we get, we have x squared times y prime plus 3x y squared times y prime. That's on our left side now. And then this is equal to 2 minus 2xy minus y cubed, everything that we moved over to the right. All right, so all the terms on the left have a y prime, so we're guaranteed that we can actually factor out a y prime from the left side. We did it specifically. We took all the terms with a y prime and we put them on the left. So we know all of them have a y prime, so we can actually factor that out. And that's what we're going to do. So we factor out a y prime, and then we just write down all of the leftover terms once we get the y prime out of there. So the first piece would have an x squared left over, and then the second piece would have a plus 3xy squared left over. So on the left, if we factor out y prime, we have x squared plus 3xy squared all times y prime. Not going to do anything to the right. Leave that as is. And then finally, we want to get y prime by itself. So we're going to take this term in front here, and we're just going to divide both sides of our equation by that term in front. So we're going to divide both sides of our equation by that term in front. And so when we do that, we get y prime by itself on the left. And then that 2 minus 2xy minus y cubed is going to become the numerator. And then in the denominator, we're going to have that term that we're dividing by, the x squared plus 3xy squared. And there we go. We have our derivative, y prime. And that's about as far as we can simplify it. And it's perfectly fine that it's in terms of both x and y. So for most of these implicit derivative problems, the derivative will be in terms of x and y, and that's okay. So we found what y prime is. Now let's use that to actually find what the equation of the tangent line is at a particular point. All right, so we're interested in the point 3, 1. So our x-coordinate is 3, our y-coordinate is 1, and we want to calculate the slope of our tangent line, and this is where the derivative comes in. So we're going to take the derivative we just calculated and evaluate it when x is equal to our x-coordinate and when y is equal to our y-coordinate. So if we fill in the derivative we just calculated, 2 minus 2xy minus y cubed all over x squared plus 3xy squared. And we're going to evaluate that when x is equal to 3, because we're at the point 3, 1, and when y is equal to 1. Our y-coordinate is 1. All right, so we go to our equation, and wherever we see an x, we're going to be plugging in 3. So we get 2 minus 2, and then instead of x, we're going to plug in 3, and then instead of y, we're going to plug in 1. So we get negative 2 times 3 times 1. Then we have minus y cubed, but instead of y, we're going to write 1. So it'll be minus 1 cubed. And then in the denominator, x squared, instead of x squared, we'll plug in a 3. So we get 3 squared. Then we have plus 3, and then 3 times 1 squared. So wherever we have an x, we're plugging in 3. Wherever we have a y, we're plugging in 1. And if we do the arithmetic here, we end up with negative 5 over 18. So there's our slope of our tangent line. All right, so we have those 3 pieces now, and we actually want to write down the equation of our tangent line. So our tangent line, and in fact any line in general, the equation is y minus the y coordinate is equal to the slope times x minus the x coordinate. So we just fill in the pieces that we have. Y coordinate is 1. Slope is negative 5 over 18. And then our x coordinate is 3. So we get the equation y minus 1 is equal to negative 5 over 18 times x minus 3. And if we simplify, distribute the negative 5 over 18 and then add 1 to both sides, we end up with y is equal to negative 5 over 18 times x plus 5 over 6 plus 1. And simplifying it just a little bit more, we get negative 5 over 18 times x plus 11 over 6. And that's our fairly standard y equals mx plus b form for our tangent line. And we can see we have our curve plotted here. So this is a graph of our curve. And we were interested in the point 3, 1, so we have that plotted. And our tangent line is drawn, and we see that it's moving downward. So that tells us the slope is negative, so that agrees with our result. And if you're looking at this curve, the curve in general does not define a function. We have to be a little bit careful with our curve. And so when we're thinking of y as an implicit function, we're really only thinking of it as a function around that point that we're interested in. So right around that point 3, 1, y, variable y, is a function of x. All right, let's try another example. We're going to do same thing, implicit differentiation. So we want to find y prime. And it's a sign that we're going to use implicit differentiation because our equation is not in the form y equals. And it turns out this equation is very difficult. I don't even think it's possible to solve to get a form y equals. So implicit differentiation really is the only way we could calculate the derivative dy dx regarding this equation. So that's what we're going to do. We're going to use implicit differentiation. So first step is we write down our equation. And we're going to apply the derivative to both sides. So we apply it to all the terms on the left and on the right. And then we're going to differentiate each of those. And when we look at this, the right side, we see that it's a product of x's and y's. It's y squared times cosine x. So when we do the derivative on the right, we're going to have to use product rule. And on the left, we see that we have an outer function, sine, and we have an inner function, the x plus y. So when we have an outer function and an inner function, something plugged inside of another function, that's an indication that we're going to use the chain rule. So we're going to use the chain rule for differentiating this sine function, and we're going to use the product rule for differentiating that right-hand side. So let's see how the chain rule part's going to look. So we start by differentiating our outer function. So derivative of sine is cosine. We keep the inside function exactly the same, so it stays x plus y. So we have cosine x plus y. Then we take those terms that are inside the parentheses and we multiply by their derivative. So that's the chain rule part. So derivative of outer function, derivative of sine is cosine. Keep what we have inside exactly the same. So it stays cosine of x plus y. And then we multiply by the derivative of those inner functions, x plus y. On the right-hand side, we're doing the product rule, y squared times cosine x. So we write down our product, 2 copies of our product, y squared times cosine x, y squared times cosine x. Put a plus sign in the middle, and then in the first copy we differentiate the first part, and in the second copy we differentiate the second part. So we've applied the chain rule, we've applied the product rule. Now we keep going and we differentiate each of those terms in the brackets, and now these are more basic ones. So the cosine x plus y is outside the brackets, we're done with that. Then for the x plus y, derivative of x is 1, and then the derivative of y is 1, but then we multiply by y prime. So the derivative of x plus y is 1 plus y prime. You know, technically there's a little bit more steps that we could do there. So if we were doing x plus y and we were doing the derivative of that, we would do, say, the derivative of x plus the derivative of y. And then the derivative of x is just 1, and then the derivative of y is 1 times, and then we multiply that by y prime. So that's where we're getting the 1 plus y prime there. But we don't necessarily need to show those steps. All right, so that's the left. Then we go to our right. Want to differentiate y squared. It's a y term by itself, so we just differentiate it like usual, then multiply the result by y prime. And then the cosine x is outside of the brackets, so that just stays cosine x. Then we have plus y squared. Y squared's out of the brackets, so that just stays a y squared. And then we differentiate the cosine x. So derivative of cosine x is negative sine. And that's just an x term, so there's nothing more we need to do there. All right, so we're done differentiating. And so now what we need to do is we need to try to solve for y prime. And before we get there, let's just clean this up just a little bit. We're going to do a little bit of arithmetic algebra here just to get it in a form that we can more readily solve for y prime. And what we're going to do is we're going to take this cosine x plus y and we're going to distribute it to the 1 and we'll distribute it to that y prime. We're going to do the multiplication there. So when we do that, we get cosine of x plus y times 1. I'm not going to write the times 1. Then we get cosine plus cosine of x plus y times y prime. That's on the left. Then on the right, we have the 2y times y prime times cosine x minus y squared times sine x. All right, so there's our equation. And now we want to go through and we want to identify all of the terms that have a y prime. So we see one right here. This one has a y prime in it. And then we see one right over here on the right side. This one has a y prime in it. And we want to get all those terms over to the left. So in order to do that, we're going to move this 2y y prime cosine x term. We're going to subtract it from both sides. And that will allow us to move it over onto the left-hand side. Now, that cosine x plus y term, there's no y prime there, so we want to move that to the right-hand side, so we're going to subtract that from both sides. So we're just moving all the terms with y prime to the left, and we're moving all the terms without y prime, we're moving those to the right. So when we do that, we get cosine of x plus y times y prime minus 2y y prime times cosine x. And then on the right-hand side, this is going to be equal to negative y squared times sine x minus cosine of x plus y. So all the terms on the left now have a y prime in it. So we're guaranteed that we can actually factor out a y prime on the left. So we can factor out y prime. And then let's just write down all of the leftover terms. So from the first piece, we would have a cosine x plus y left over. And then from the second piece, we would have a negative 2y cosine x left over. And all of that's times y prime. And then for our right-hand side, nothing over there yet. We're just going to leave that as is. So just negative y squared sine x minus cosine of x plus y. All right, so last step then is to take this term in front now and just divide both sides by it. So to get it over to the other side so that we have y prime by itself. So if we do that, we get negative y squared sine x minus cosine x plus y on the numerator. And then in the denominator, we end up with cosine of x plus y minus 2y of cosine x. And there's our derivative y prime. And again, perfectly okay that it's in terms of x and y. And we have a graph here. So this is the graph of this curve. And so if we just take the curve as is, again, it's y would not be considered a function of x. But for implicit differentiation, we have to be a little bit, or for implicit functions, we tend to be a little bit more careful, and we restrict our attention to, say, a point that we're interested in, and then right around that point, the curve is behaving like a function. So right around that point that we're interested in, it would make sense to talk about the derivative, the slope of the tangent line. So right around that point, we actually can think of y as a function of x. All right, so practice, practice, practice. Let's try one more of these implicit differentiations. So here we're going to look at the equation x to the fourth plus y to the fourth equal to 16. And we're actually going to see how to do the second derivative. So in our little graph here, just an interesting observation, really. x to the fourth plus y to the fourth equal to 16 is sort of that squarish looking circle. And then we've also graphed here x squared plus y squared equal to 4. And that's just our regular circle there in the middle. So, as the exponents increase, so x to the fourth plus y to the fourth, you still get something resembling a circle, but it becomes a little bit more boxish. It starts to look more like a square. So if you had like x to the 100 plus y to the 100 equal to 2 to the 100, if you were to graph that equation, you would get something that looks very much like a square. So just an interesting observation. X to the fourth plus y to the fourth equals 16, sort of like a circle, but it looks a little more boxy. But regardless, we can talk about the slope of the tangent line at points along that curve, so it makes sense to talk about the derivative y prime. So we're going to calculate y prime. So we write down our equation, x squared plus y to the fourth equal to 16. We apply the derivative to both sides. Every term on the left, every term on the right. The x to the fourth, there's only an x there, so when we differentiate just like usual, so 4x cubed. The y to the fourth, when we differentiate that, there's only a y there, so we differentiate like usual, and then multiply the result by y prime. So we get 4y cubed times y prime. And then on the right, it's a constant by itself, so derivative of 16 is just 0. And then from here, we want to solve for y prime. So all the terms with y prime we keep on the left, and then everything without y prime we move to the other side. So to do that, we would subtract 4x cubed from both sides. So that gives us 4y cubed times y prime is equal to negative 4x cubed. We factor out y prime on the left. So we think of this as 4y cubed times y prime. And then we just divide both sides by that term in front. So 4y cubed divided by 4y cubed. We divide both sides. And that gets us y prime by itself. So we have y prime by itself on the left. And then if we simplify those terms on the right, the 4's cancel, and we're left with negative x cubed over y cubed. All right, so there we've simplified y prime really as much as we can. So the main part here is we're interested in finding the second derivative, y double prime. So far we've only found the first derivative. So to get the second derivative, once we have y prime there by itself, we just differentiate again. And that's what we're going to do in step 2. So to get the second derivative, we take our first derivative and just differentiate it. So we take our first derivative, which is negative x cubed over y cubed, and we're just going to apply the derivative. So when we do the derivative of y prime, that's going to give us our second derivative, y double prime. And then on the right there, it's x cubed divided by y cubed. So there's x term, both x's and y's, and it's a fraction, so we would have to use the quotient rule. So we'll leave the negative in front, and let's implement the quotient rule. So we write down our quotient, top times bottom. So we write it as a product, top times bottom. 2 copies, top times bottom. And then we put a minus sign in the middle there. And then in the first copy, we apply the derivative to the first function. In the second copy, we apply the derivative to the second function. And then we divide all of that by the original denominator squared. So y cubed squared. Then we keep differentiating. So derivative of x cubed, it's just an x term, so we differentiate that like usual. So 3x squared, and then we have our y cubed, and then minus our x cubed. Those are outside of the brackets, so we were done with those. Then we differentiate y cubed. So derivative of y cubed is 3y squared, and then we multiply that result by y prime. So it's just a y term there that we're differentiating. So the derivative of y cubed is 3y squared multiplied by y prime. And then all over, and we maybe simplify the denominator just a little bit. So y cubed squared, when we have multiple exponents like that, we multiply them. So we would get y to the power 6. So there's our second derivative. The only issue here is we have this y prime term here that we want to get rid of. And so we don't want y prime in our expression for y double prime. But we know what y prime is, so we can fill that in. We know that it's negative x cubed over y cubed, so we can fill that in. And we maybe just clean up a little bit there. And so now we have our second derivative all in terms of x and y, so that's good. But we could try to simplify just a little bit. That might be helpful. So I'll leave the negative in front. And nothing yet to do with that 3x squared times y cubed. And in that second term, we're going to have a double negative, so it's going to become positive. And we have x cubed times x cubed. So that'll become x to the power 6. And then we have y squared divided by y cubed. So that will become 1 over y if we simplify that down. And I think I missed the 3 there. So we had a double negative, and then we also have a 3. So it'd be plus 3 times x to the 6 times 1 over y. All right, so there's our derivative simplified, second derivative simplified down a little bit. Clean it up just a little bit more. We want to get rid of that 1 over y term in the numerator. And so the way we can get rid of that is by multiplying by a fancy 1. So we can multiply both the top and the bottom by y. And so we'll distribute the y to the first term. We'll distribute the y to the second term, and then we'll also distribute into the denominator. So when we do that, we get negative 3x squared y to the 4th. And then when we distribute to the second term there, the y and the 1 over y cancel. So we're left with just 3x to the 6th. And then we have y to the power 7 now in the denominator. And that's looking better. You know, technically we could have stopped way back here. So we could have stopped way back here. This was perfectly fine. But you want to try to simplify as much as you can, just to help clean things up, simplify it if you have to plug in or anything like that. And we can actually go a little bit further. We can factor out a 3x squared on the numerator. So we're left with just y to the 4th plus x to the 4th all over y to the 7. And then that x to the 4th, y to the 4th, we know what that's equal to. It's equal to 16. So this ends up being negative 3x squared times 16 over y to the 7. And if we go just a little bit further, the 3 and the 16, multiply those together, that would give us 48. So we get 48x squared over y to the 7. So there's our second derivative, simplified down quite a bit. All right, so that's implicit differentiation. And for our next kind of topic here, we're going to use implicit differentiation to prove a lot of our elementary derivative forms. And so that's the next topic we're going to be considering. We want to prove a lot of those elementary form derivative formulas using either product rule, quotient rule, chain rule, or this new technique of implicit differentiation. So let's just remember what our elementary forms are. We had all our trig functions, our inverse trig functions, exponential log functions, and really the three basic derivatives here that we're going to use to prove all of the other ones are the derivative of sine, derivative of cosine, and then the derivative of e to the x. And we're going to see how to prove all of these functions, all of these derivative formulas using just those three derivatives. And so we can show the rest of these trig derivatives using just product rule, quotient rule, or chain rule. So if you forget the formula, it's not the end of the world. You might be able to just cook it up on your own. So we can prove those using just product, quotient, or chain rule. Same thing with the derivative formula for b to the x. This one we can do with just chain rule. Now for our inverse trig functions and for our log functions, and really inverse or log is really just an inverse exponential function. So for these inverse functions, all of these can be proved using implicit differentiation. We'll see how to do this. So basically, I would still recommend memorizing these derivative formulas. You don't want to have to prove them every single time. But really, these elementary forms come down to just knowing sine, derivative of cosine, and derivative e to the x. So let's try, we'll get started. We'll try derivative of tangent. So let's use derivative rules to show that the derivative of tangent x is equal to secant squared x. And we don't get it for free. We still have to remember something. And the thing that we have to remember then is, well, how is tangent defined in terms of sine and cosine? So we have these formulas for how our 6 trig functions are related to sine and cosine. So there's sine and cosine just as is. Tangent turns out is equal to sine over cosine, and that's what we're going to use. So when we differentiate tangent x, if we use that relationship, tangent is really just sine x over cosine x. That's what we're going to differentiate. We have a fraction. There's x terms on the top. There's x terms on the bottom. And we're going to apply the quotient rule. So let's implement the quotient rule. So it's top times bottom, so 2 copies. Put a minus in the middle there. In the first copy, we apply the derivative to the first function. In the second copy, we apply the derivative to the second function. Then we divide and we square the original denominator. So we know the derivative of sine is cosine, so we fill that in, cosine. So we have cosine times cosine, then minus sine of x. And then the derivative of cosine x is negative sine of x. And all of this is over cosine x squared. If we simplify, the numerator there becomes cosine squared x plus sine squared x all over cosine x squared. And cosine squared plus sine squared is a trig identity that's equal to just 1. So this is one of our very common trig identities, that sine squared theta plus cosine squared theta is equal to 1, related to Pythagorean theorem. So the numerator there, cosine squared x plus sine squared x, just becomes 1. So we're left with 1 over cosine squared x. And maybe I'll keep that as how I had it before. And so we could really think of this 1 over cosine x squared as 1 over cosine x, the whole fraction squared. And then 1 over cosine x is secant. So this would be secant x all squared, which is just secant squared x. So a lot of times we simplify so we don't have to use so many parentheses. We put the squared on the trig function, directly on the trig function. So that's just kind of a notational thing that we do just to simplify so we don't have so many parentheses. Yeah, so we had 1 over cosine x squared. We kind of wrote that as 1 over cosine x, the whole fraction squared. And then we just identify that 1 over cosine x is equal to secant x. So 1 over cosine x is equal to secant x, and then we get secant squared. All right, so we'll see more of proving these elementary forms next time. And in particular, we'll come back and we'll use some more implicit differentiation to try and prove those inverse trig in log rules that we've been working with so far. We're actually going to prove those next time. All right, so we'll stop there. Have a good rest of your day. Remember recitation if you have questions on the homework. And then we'll see everyone for lecture on Thursday. Bye-bye.